Hello everyone, welcome to Organic 2 Labs Friedel-Crafts Acylation experiment. This experiment is a version of one of the possibilities for electrophilic aromatic substitution. Specifically, something to kind of keep in mind here, you will be using aluminum chloride in this reaction. And so there's some safety information that you want to pay attention to with that. Also, you will be using an unknown benzene derivative. It's either going to be anisole, toluene, or ethylbenzene. So that's going to be something to also kind of keep in mind here with this reaction. All right, so what we see with Friedel-Crafts acylation, this is a way that we can get some type of carbon chain or carbon structure. It's typically going to be a chain, but how we can get it on a benzene ring, all right? And so we are following kind of the suit with, we're going to see something like a benzene or a benzene ring derivative acting like a nucleophile and interacting with an electrophile. And so for us, we need to pay attention to what our electrophile is. All right. Also, things to kind of remember, especially from the last experiment, since you are going to be using not benzene but one of these three derivatives, you do want to kind of keep in mind electron donating versus electron withdrawing groups. How do they work? What do they do? All right. Now, with looking at Friedel-Crafts, right? There are two Friedel-Crafts reactions that fall under the electrophilic aromatic substitution. There's an alkylation and an acylation. All right, so with an alkylation, you're going to start with aluminum chloride as a catalyst, and it's going to react with some type of alkyl chloride. All right, so here you have one chloroethane. All right, and so with that, you're actually going to turn this ethyl chloride into, or chloroethane, however you want to think about it. You're going to turn this ethyl chloride into a cation and a carbocation electrophile, and then the benzene will act as the nucleophile, and we'll see that in a second. Now, what you can see here is one of two main problems we're going to focus on with Friedel-Crafts alkylation, all right, pay attention, I am talking about alkylation, is that it doesn't necessarily stop once it does the reaction the first time. It will go and do it a second time. So then you can have ethylbenzene as a product. You could then have as a mono substituted. You could then have di-substituted products, and it could be so bad that you would get into where you have the mono. You have the mono here, all right? You could have the di. You could even have the tri, all right? It can just try to keep going, okay? And remember, if you pay attention specifically here in the di-substituted, all right, if we start with this, we're going to then add this again a second time. And so remember, this ethyl group is an activating group. It's an activating group, and it's also an ortho-para director, right? OP director. And so you notice if, say, that was the first one, right? The second one here can go ortho, or it can go para, and or both, right? So that's why we see the di substituted looking like this. Now with the tri substituted, we're going to have to give up something here. But if we look at with retrospect as this one being the first one, we had both an ortho and a para that was added. Okay, so that's one of the big problems with Friedel-Crafts alkylation. Okay. Now, there's also an additional problem that can occur with Friedel-Crafts alkylation, where you can have carbocation rearrangement take place. Okay, and so here we go. You can have rearrangements of that alkyl group, or a carbocation rearrangement. And so specifically what we're referencing here for this rearrangement, you want to think of things a very certain way. So kind of looking at this same reaction, I've just elaborated a little bit more on the mechanism to try and help explain this. So what do we see happening here? All right, so looking at the reaction, right? So if we start with here we have 1-chloropropane with the aluminum chloride. So remember, for electrophilic aromatic substitution reactions, let's think of these two reacting first, right, to create our electrophile. So you're going to see the lone pair of the chlorine attack the aluminum, and so you're going to have this aluminum chlorine bond. And so to make things kind of make sense to you in terms of a rearrangement, why do these happen? Think of this carbon chlorine bond breaking, and so you see here you make a primary carbocation, right? And that in essence turns into AlCl4 minus, right? Um, and so anyway, once you make this primary carbocation, we know that primary carbocations are not very stable. So it can undergo a rearrangement in the form of a hydride shift, right? The hydrogen and the electrons in that bond right there are going to move to this carbon position and give us a secondary carbocation, and that's more stable. And so that the big problem here is both of these could happen, right? Because as soon as you make this electrophile, now the benzene can start coming in to react. And you can imagine if you put in an extra group, right? Say you put in an electron donating group, it makes it more activating. It reacts even faster than just benzene. So in essence, what you have happening here is two electrophile possibilities. You no longer have control, and so you can see benzene reacting with the primary carbocation to give us this product, the propyl product, or you could see it and you can see it reacting with the secondary carbocation to give us the isopropyl product. Okay, so that's one of the big problem. That's the second huge problem, right? You lose a lot of controllability, or a lot of control. I don't think controllability is a word, but you lose a lot of control with Friedel-Crafts alkylation in terms of what products are formed. So that's why we prefer to look at something like Friedel-Crafts acylation, where now you no longer have an alkyl halide, you have this acid chloride, right? And you're still going to be using aluminum chloride as your catalyst, but you have a lot more control. You're not going to see polyalkylations or acylations, right? You're going to see one product, right? And you're not going to see rearrangement. Okay, so this is a lot more controlled. And so what is really happening here in this reaction? So in this reaction, all right, things are going to happen similarly to Friedel-Crafts alkylation, not exactly the same, but similarly. All right, so what you're going to see happening here, let's look at the acid chloride and aluminum chloride reacting first. So you're going to see this carbon-chlorine bond breaking to where the chlorine is now going to be attached, or the electrons here are going to attack the aluminum. So you have AlCO4 minus, and then since you have this pi bond here and the lone pair electrons on the oxygen, you can see one of the lone pair move down here so that you can have some imparted stability. Because remember, this right here is resonance stabilized, right? This pi bond could move back up. So in essence, you do have two possible structures. Right? So you do have that as a possibility. Okay, so it's resonance stabilized. Now, with that, it being resonance stabilized, you're not going to see any type of rearrangement, nothing like that's going to happen. So then when your benzene or your benzene derivative, because you won't be using benzene, but when your benzene comes in, it's going to act like the nucleophile now, and it's going to attack the carbon here of this, well, once was the carbonyl carbon, but it's going to attack the carbon here, pi bond will move up, and so then you're going to see the formation of your rhenium ion, okay? And then like we see with most of our what we've seen so far with all of our electrophilic aromatic substitution reactions, we do have to regenerate our catalyst, so we have to go back to aluminum chloride, AlCl3. So we're going to see the aluminum chlorine bond here donate and take off this hydrogen here so that we can get a pi bond back in our ring and we can be aromatic all over again. All right, and so no rearrangements, no polyacylations. All right, so those are the two really great things about this. Now, you may not want this carbonyl here, and that's fine. You could easily remove it and reduce it, get two hydrogens on that carbon position, and you could use something like zinc mercury amalgam, or you could use You could use like a Wolff-Kishner reduction. All right, so these would work. And so in essence, if you use one of these with this, you would just turn it into that. Okay. All right. Okay. Now, some things to keep in mind here as we move through. Safety. All right, you are using aluminum chloride. It is water sensitive. It's an irritant and it is corrosive. Okay, one of the big reasons I want you to remember this, in this reaction, aluminum chloride is acting like a catalyst. So yes, it does initially get used up, but then it gets recreated, right? We regenerate that catalyst. And so when we regenerate it, you're going to have the possibility of some aluminum chloride in your separatory funnel. Why is this bad? If you do not follow these steps of your procedure, right? Specifically, when we start right here, going from here to here, if you do not follow these steps very carefully, right, you could have an eruption occur with your separatory funnel. All right. And with that eruption, why is it so bad? Well, not just the fact that there's organic solvent in there, DCM, there's also hydrochloric acid that could be in there. And you guys know that acid burns. So, follow these steps very carefully to avoid any issues. I wonder why I highlighted this whole segment and I keep talking about it. Anyway, so now the big thing here, I told you that you're not going to know what benzene derivative you're using. You will have one of these three, either anisole, toluene, or ethylbenzene, right? And so when we look at these three, all right, so when we look at these and you're doing your Friedel-Crafts acylation, right, you're going to be using one of those three. So anisole, toluene, or ethylbenzene. So think about these groups. Are they electron donating? Are they electron withdrawing groups? So where will your acylation take place on the benzene ring, right? Where is it going to happen? Most likely. Okay. Now, another thing, you're going to have to evaluate once you do your Friedel-Crafts acylation. You're going to take IR for the product. And so think about what characteristics would you see in IR. Specifically, when you look at, there's R group. So whether it's anisole, whether it's OCH3, an ether functional group, methyl, or an ethyl functional group, what's going to be the huge difference here? Okay, hopefully you're looking at that. So you have to think about where are you going to see that in IR, right? You don't have a carbonyl over here, you do have a carbonyl over here. So that's going to be kind of your proof in the pudding that you were successful in doing this reaction. Okay, you will also be given a set of spectra based off of what your unknown was. You have either unknown X, Y, or Z. So do be ready for that. Okay, now, one other thing. You do have to do theoretical yield calculations and percent yield calculations for this reaction. So, let's say you had anisole as your unknown benzene derivative. You are told, right, and I'll prove it, you are told here the density of the three unknowns. You're going to have to use this to figure out what mass or how many moles of these guys you had. So, looking at kind of an example really quickly here. If you had anisole, we know the molar mass of anisole. We could easily calculate that based off the number of carbons, oxygen, and hydrogens. And then you're given the density. So here, for those theoretical yield calculations, you'll need to take milliliters, right? Because you were told to measure out a certain volume. It's not 4 milliliters, so don't think I'm giving you any answers here. But you're going to have to take milliliters and convert it to grams or moles. Okay, so how are you going to do that? So starting with your 4 milliliters, first how do you get the mass, then how do you get the moles? So when you start with your 4 milliliters, that you measured out in the graduated cylinder, you can just use the density, right? Grams over, so it's 0.995 grams per milliliter, right? So that's the same thing as saying 0.995 grams per 1 milliliter. So if you multiply it like so, your milliliters units will cancel and you'll get your mass of grams of anisole. Now, if you need to go to moles, you need to add a step, right? So you're still going to take your volume, you're going to multiply it by the density, but now you need to get that molar mass, all right? And in this case, 1 mole of anisole is 108.14 grams. So when you set it up like this, multiplying it like this as a fraction, that's how you can get your moles. Okay, so keep that in mind for when you have to do your theoretical and percent yield calculations. All right, you should be prepared for your pre-lab quiz. Good luck.